representation for floating point numbers. We have, as we discussed, we have single precision, which takes 32 bits, and we have double precision, which takes 64 bits. Okay, so in C or C++, this single precision number is shown as float, and the double precision is shown as double. Okay, so now out of this 32 bits, we have 1 bit for the sign. In single precision, we have 8 bits for the exponent and 23 bits for the fraction. In the double, we have 11 bits for the exponent and 52 bits for the fraction. And if some number is stored like this, then the actual number which we are storing here is found as this: x equals to -1 raised to power s into 1 plus fraction into 2 raised to power exponent minus pi s. So this 1 bit is always hidden.
Sir, your screen is not shared, sir.
Sir, your screen is not visible.
Sorry for that. Okay, so in single precision, we have 8 bits for exponent and 23 bits for fraction. In double, we have 11 bits for exponent and 52 bits for the fraction. Now, if we store any number like this, then the actual number that we have is the following: x equals to -1 to the power s. That means if s is 0, then it is a non-negative number. If s is 1, then it is a negative number. And we have 1 plus fraction. That means the original number had a 1 in front of it, but we are not explicitly storing the 1. Okay, so because we always have this 1, we will not store this 1 explicitly, because we have normalized our number to the range between 1 to 2. Okay. Now, so our significant is fraction with 1 restored. And another thing is that exponent that we store is in the form of excess exponent. That means whatever exponent we have, we add a bias to it. Why we add the bias, I will show in just a moment. But one thing is it ensures that the exponent is unsigned. That means we always make sure that our exponent is unsigned. And for the single precision, our bias is 127. For double precision, our bias is 1023. Okay. So now let us try to answer why we use the bias. Suppose I don't use the bias. Okay, suppose I don't use the bias. Now I will use only unsigned exponents here in 8 bits. Okay, I will only store the unsigned exponents. So unsigned means my lowest number is 0. Right? My lowest number is 0. So right now I'm setting bias to be 0. That means I'm not using the bias, means I'm setting the bias to be 0. Suppose this is 0. So my exponent can be minimum values 0 for single precision and maximum value is 255. Isn't it? Because we have 8 bits. So with 8 bits, the maximum number I can store is 255. Is it fine for everyone? Okay. So now so this is the case if I do not use the bias. Now, if I use the bias, then what is the range I can store? So bias is 127. So you subtract 127. And here also you subtract 127. That means minus 127 to, isn't it? So now I can store this range. Okay. So if I don't use the bias, I can store this range. If I use the bias, I can store this range. So now you tell me what are the pluses and minuses of each of them, either this case or this case.
So in first case, our range is higher, but in second case, we are also including negative powers also.
Yes. Mohit, you want to say anything else?
No, actually, sir, this in negative range, we can represent the sign data also, sir. We can show the sign.
No, no, it is not about something. All these numbers are positive numbers. See, whether the number is positive or negative is decided by this. Here we are just taking the exponent being positive or negative, or exponent being small or large. So the point is, in this case, that means if I store between 0 to 255, I'm starting with 2 to the power 0 and going up to very, very large number. But I'm not able to store small numbers. Whereas if I use some bias, I'm sacrificing my capability to store large number, but I'm able to store small numbers. Okay, I'm able to store 2 raised to power minus 127 onwards to 2 raised to power 128, or actually it will not be 128, it will be one less than that, but just for argument's sake. So I'm able to store somewhat beginning with smaller number. I don't go as far as 255, but at least I go till 2 raised to power 128. So it's more important to store small numbers rather than to just go on storing large numbers. Otherwise, I will not be able to store them accurately. Okay, so this is the benefit of bias. It allows us to store smaller number at the cost of not being able to store large numbers. Now, let us see more discussion. So let us see what is the range. Range means what is the smallest and largest number that I can store. So first thing is the exponent being all 0 and exponent being all 1, that has a special meaning. So that is reserved for a purpose. All right. So this is reserved for a purpose. So what is the smallest value I can store is when the exponent value is, what is the smallest value you can store in FP32? So exponent is when my exponent is just 1. So my actual exponent is minus 126. Because if this is the exponent that I saw, that means actual exponent was this, and I had added a bias of 127 to make it plus 1. And fraction can be all 0. So our significand is 1.00000. So that is all 1. So the number actually I can store is this 1 into 2 raised to the power minus 126, which is equal to this number. That means 10 raised to the power minus 38. And the largest value I can store is when exponent is this minus 1. Okay, I can't store all bits being 1 because that has a special meaning. So I can only store exponent where this minus 1 is there. So actual exponent is 254 minus 127. So actual exponent is 127. And because I'm finding out the largest value, so my fraction can be all 1. Okay, so that means my significand is almost close to 2. So, so the largest number I can store is 2 into 2 raised to the power 127. So, which is equal to this. So that means beginning with 10 raised to the power minus 38 to almost 10 raised to the power plus 38. This is the range of numbers I can store. Similarly, we can do this analysis for double precision. Exponent's value of all 0 and all 1, that is reserved. So the smallest value I can have is when exponent is just 1, which means my actual exponent is 10 raised to the power minus 1022, and fraction can be all 0. So my significand is 1. So the smallest value I can store is 2.2 into 10 raised to the power minus 308. And the largest value you can store is all bits being 1 except the last one. So actual exponent is 1023. And fraction can be all 1. So my significand is almost equal to 2. So the largest number I can store is 2 into 2 raised to the power 1023. Okay. So which is equal to 1.8 into 10 raised to the power plus 308. Okay. So here you can see the range is much larger than it was in the single precision. Here it was only 10 raised to the power minus 38 to plus 38. Here it is 308 to plus 308. Now, why it is called single precision or double? So please understand how we have done it. We will ask you to do this kind of calculation for some arbitrary, number system. So you must have understood this. If you could not understand, please go back and read it yourself then ask me the question if you have. Okay. So now why it is called precision? Precision shows the number of decimal digits that are correct. That means we can use them without any kind of representation error or approximation. In other words, it shows how many decimal digits we can safely use. Okay, so in single precision, we have almost 7 or 8 decimal digits. Why? Because see, we have 23 bits for the fraction here. Okay, we have 23 bits of fraction here, and 1 is hidden. So 1 plus 23, we have almost 24 bits. Right? We have 24 bits. So 2 raised to power 24, and if you take log 10, which is almost 7 to 8 decimal digits. And in the double precision, we have 52 bits here plus 1 bit here, so total of 53 bits. So which means I have almost 15 to 16 decimal digits that I can safely use. So here you can see this is almost double of the previous case. Okay, 7 to 8. If you double it, it is almost 15, 16. That means for some numbers it will be 7, for some numbers it will be 8 decimal digits that are reliable. Okay, and now if you go back to the tutorial 1 that I had given, where we had given Newton-Raphson code, right? Where if you use float, you can only go up to certain precision. Whereas if you use double, you can go much better precision. Now you see why that was failing with float. Is it? Do you remember that question? Anupam is here. Anupam, or anybody can tell. Anupam, you remember that tutorial question 1? I mean the question on Newton-Raphson.
Sir, yes, sir.
So I can open that again if you want. I can.
Sir, I'll have to check, sir.
I have it here. 1, 2, 3, and 7. Okay, I have it here. I will share it with you. Just a moment. If I share the screen, so here you can. Okay, you can see this part. Everybody can see this.
Yes.
So here, see, we had 3 and 3, 7. So we had only 7 digits after decimal. So it converged. But when we went to 8, 4 and 4, 8, it did not converge. Okay. So because it went outside the range of single precision. Whereas with double, the same thing converged. See, the reason it was not converging it is that actually it is. We are trying to go very close, but our precision does not allow us to go that close. That's why it was failing. Okay, so that's the reason it was failing. So okay, now any question from some student? Okay, so this I will explain actually later. I will show this point through a solved example. Then this will be more clear. Now, how do we find accuracy of FP32? I think we have that range here. So we have shown. I have shown you the range. Now let us talk about the accuracy. So with the smallest number I can represent is this. The next smallest number that I can represent is this. Okay, the next smallest number. Now, if we find the difference between them, we call it a delta. And if we find delta into 100 divided by smallest number into 2, this gives us the percentage accuracy. And that percentage accuracy is this. Okay, the percentage accuracy is this. So that's the idea. So of course, I will not ask you to calculate the accuracy, but just to show you how did we calculate this accuracy. You can actually do it very easily for FP16 because FP16 numbers are not so large. I will give you that as a homework exercise. Okay, you have to find the smallest representable number using FP60 and the next smallest, that means slightly higher. And then find out the difference between them, call it delta, then calculate delta into 100 divided by smallest number into 2. And as I said, there is also this brain floating point BF16, which is becoming popular. So here the range comes same as FP32. Why? Because they've used larger exponent larger number of exponent bits. But Mantissa bits are small, very small. So that is a disadvantage. Okay, I will give you a small. I'll show you a solved example today itself. That will make things more clear. Just let us do some more things, then I will come to the solved example. So suppose we want to represent this number in single precision number system. So we represent it like this. So here it is minus number, so we put it like this. Now we write it as 1.1. So 1 is, this is 1, and this is equal to how much value? 1.5. So in decimal, this 1.1 in binary is equal to 1.5 in decimal. Do you agree or not?
Sure.
Okay, because I hope you have I hope you know that much digital logic. So now we write our fraction because this 1 is hidden. So we will not represent. So we'll just represent this. So 1, 0, 0, 0. And our actual exponent is -1. So we'll add the bias to it. So we add bias of 127 or 1023 here. So this becomes 126, which will store like this. And the double becomes this. So in the single precision, we have this sign, which is 1. Then we have 126 or 1022 here. And then we have the fraction, where only one bit is 1, remaining bits are all 0. And if you want to do the opposite, we find out that, okay, this is a negative number. And the exponent that we have stored is 129. That means our actual exponent is just 2, 129 minus 127. And our number is 1.01 in binary. So what is this in decimal? 1.01 in binary is how much in decimal?
$1.25.
1.75. 1.
Sagar?
Sir, 1.25.
Yes, yeah, 1 point. That's the number. Yeah, because this 0 is equal to 1. This is equal to, I mean, the weight of this bit is half. The weight of this bit is 1/4. So this is 0, so we don't count it. This bit is 1, so we count it as 1/4. That means 0.25. So that is 1 is here anyway. So 1.25. So we calculate this as 1.25 into 2 raised to power 2. Okay, so that becomes -5. Now we will also introduce d-normal numbers. So what are d-normal numbers? So here I showed you that this was 10 raised to power -38, something into like some 1 point something into 10 raised to power -38. And this number was 10 raised to power +38 for single precision. Now still we are missing many numbers between 0 to the smallest number, 10 raised to power -38. So can we also represent them? So answer is yes. We can use d-normal numbers. Okay. So in d-normal numbers, so this is for FP32, our exponent is all 0, right? And previously we said that exponent being all 0 is reserved for something. We said that it is reserved for something. Now I'm telling you for what it was reserved. It is reserved for d-normal numbers. So here it is all reserved for 0. So that, and here whenever it is exponent is all 0, the hidden bit is not 1, but hidden bit is 0. Okay, so this hidden bit is 0. So that 0 comes here, not 1. And then we have fraction here. And here we don't do 0 minus 127, but we do 1 minus 127 always. So here this will always be for all the d-normal numbers. This exponent becomes minus 126. That is fixed. So these are the two different things you have to memorize. This is 0 and this is minus 126. So all the d-normal numbers are smaller than the normal numbers. So we call these numbers as normal numbers, these numbers as d-normal numbers. So these d-normal numbers, they are smaller than normal numbers. They allow for gradual underflow with diminishing precision. So that means instead of not being able to represent the d-normal numbers, we are able to at least represent them with less precision. Right? Instead of calling them all 0, we are able to at least represent them with some precision, but not very high precision. And as I already said, for d-normal numbers, this number is, if you calculate it as 0 minus bias, you will reach a wrong answer. So here you have to use 1 minus 127, which is minus 126. That is an exception. Okay. So here in d-normal numbers, as we said, the smallest positive normal number was 2 raised to power minus 126. That we have shown here. The smallest value of positive normal number was 2 raised to power minus 126. Okay, so that was the smallest positive normal number. And what is the largest d-normal number? Where my here you can see the hidden bit is all 0. Now the fraction can be all 1. Okay, and this is 2 raised to power minus 126. So the largest d-normal number is this is 0, hidden bit is 0, then all of this bit is 1, and 2 raised to power minus 126. So this becomes 2 raised to power minus 26 minus 2 raised to power minus 149. That means compared to this 2 raised to power minus 126, we are slightly less. How much less? 2 raised to power minus 129, this much less. Okay. So this allows us to represent at least some numbers. Instead of not being able to represent, we are able to represent some numbers. And what is my range? The smallest d-normal number I can represent is 2 raised to power minus 149. So what that will be? 0.0000, all of them, except the last one. Except the last bit being 1. All the remaining bits are 0. Okay. Okay. So 2 raised to power minus 149. So that is the smallest d-normal number, and this largest d-normal number I have already shown you. Okay. So this number is 2 raised to power minus 2 raised to power minus 23. If you multiply it with 2 raised to power minus 126, this becomes 2 raised to power minus 149. That's this smallest positive d-normal number. And same thing will also be in the negative side. Any questions here? So this may be appearing a little bit, some memorization is definitely required. So but because it will be very, very useful actually even in the future, because these precisions will keep on coming, whichever accelerator you design. Not only in this course, but I think many other courses, this precision will be very much useful. So you please just memorize it. There are only two formats you have to remember. One is for d-normal, which is this one. Okay, and one is for normal, which is this one, which is this one. These are the two simple representations you have to remember, so that you can please remember them. Okay, now there are two more cases. One is infinity, another is NA, not a number. So if the exponent is all 1, and the fraction is all 0, we call it infinity. That means now the number has gone outside the range of representable number. All right. Now the number has gone outside the range of representable number. And if the exponent is all 1, but the fraction is not all 0, then it is not a number. Okay. So this indicates some undefined result. So this actually this infinity means overflow. Okay, infinity means overflow, and NaN means illegal output. That means some some really wrong, so some really big mistake has happened, which is outside the law of mathematics. For example, if you want to compute 0 plus 0, or if you want to compute sine inverse of 5, sine inverse of 5 is not possible. That's why we call it NaN. And if you do this is like very, very large number that is represented as infinity. Okay, that is represented as infinity. So again, you also have to remember these two cases. When it is exponent, when it is infinity, when it is NaN, you have to memorize it, which is not very difficult. This is exponent is all 1, fraction is all 0. That is infinity. Exponent is all 1, fraction is not all 0. Then it is NaN. Okay. So now, how many bits we have in the fraction for single precision? Please tell me.
23, sir.
23. Yeah. So how many NaN will be there in single precision? How many distinct representation for NaN we have? Assuming only positive NaNs. I mean, NaN does not have positive and negative, but you ignore the sign bit, and then you tell me how many representations.
2 power 23 minus 1.
Yes, very, very nice. Yeah. So I will ask somebody else to explain it. How did we get this 2 raised to power? So Krishna Chaitanya, can you please tell? Krishna Chaitanya, can you tell how did we get this many numbers of NaN? Okay, Ashish, you want to tell? How did we get this many NaNs? Prashant or anyone else wants to explain how did we get this many NaN? This is a simple permutation combination question.
Yes, sir.
Yes, Priyansh.
Sir, Narendra, sir.
Okay, Narendra, yes.
Yes, sir. Total number of combinations are 2 to the power 23.
Okay.
And one is reserved for 000 for infinity. So we are subtracted from that.
Yes, yeah. So this is a simple permutation combination. I think you forgot. Probably you did not read that. Permutation combination is very, very fundamental mathematics. So we have 23 bits. So those 23 bits can take 2 raised to the power 23 combinations, out of which one is not possible because one is for this infinity. So 2 raised to the power 23 minus 1. So we have so many representations of NaN. So this is just the summary of single precision. If we have all exponent bits as 1, but my mantissa or fraction is all 0, then it is infinity. And for NaN, we don't call positive infinity, negative infinity. But for NaN, we don't call positive NaN or negative NaN. But for infinity, we can call positive infinity, negative infinity. Nice. So here, if exponent is all 1, but mantissa is not all 0, then it is NaN. And if it is exponent is 0, mantissa is 0, then it is exactly precisely 0 number. And if it is exponent is 0, but mantissa is not 0, it's a d-normal number. So if you want to go further, you can study this. Especially, I think this blog is very good if you want to really understand it in depth. This is a very good blog, I guess. Yeah, one of this was I think this one was very good blog.